continue with our studies of mass transfer. What we are going to look today is a situation which is very common in chemical engineering. In some chemical engineering problems, it is taken as an assumption, and in many of the cases it is a very valid assumption. The name of that situation is Equimolar Counterdiffusion. As the name suggests, this arises when each mole of A, let us say, going in from the right to left, one mole of B will move in the opposite direction. So, in some situations, if you can maintain that condition, that for each mole of A going to one direction, another mole of B will be moving in the other direction, that situation is known as equimolar counterdiffusion. Now, why spend any time on equimolar counterdiffusion apart from it is going to give us some mathematical advantage, flexibility, while using the expression for, let us say, NAZ, that is the species movement rate from in the Z direction. Many of you have heard of distillation process, right? Distillation is nothing but if you have a mixture of two liquids and you would like to separate one from the other. Any idea how this is done? What is distillation? Okay. The simplest possible distillation apparatus that you can think of is, it's called a still. Okay. You have a container, that container contains the mixture of A and B, and you would like to separate A from B. Now, the first use of distillation column is for making alcohols. Okay. For a very long time, people know how to make alcohols from let us say a mixture which can be fermented, but it contains, among other things, two principal constituents. One is alcohol and the second is water. So, you would like to concentrate the alcohol. So, you put the mixture in a still and heat it. Now, what happens when you heat a mixture where there is a change, a difference in relative volatility? Now, what is relative volatility? We all know that each component has a specific vapor pressure. More the vapor pressure, is it easier to vaporize it or it is difficult to vaporize it? It is easier to vaporize it. So, that is why fragrances, alcohols, they have very high vapor pressure. Some of the like organic compounds, for example, pentane, benzene, toluene, they have high vapor pressure compared to water, and water has high vapor pressure compared to heavy oils. So, if we can heat the mixture of air and water and alcohol, so what would happen is more of alcohol will come into the vapor phase compared to water. So, what you do, you collect the vapor which is generated from a still containing water and alcohol. So, the vapor that you are going to get will be rich in alcohol, you condense it, and what you get is concentrated alcohol. So, this is the simplest possible single stage distillation apparatus. Now, if you think of, you know what is the difference between a batch process and a continuous process. A batch process where you charge everything at one time, let the reaction, separation, whatever, any operation continue in that, and you collect your products and then you charge another batch into the system. So, this is the simplest possible example of batch distillation, where you try to concentrate a high vapor pressure component by vaporizing it and thereafter condensing it. Now, this method has later been improved upon to make it continuous, and if you think of the still or the container containing the mixture of liquid, the two liquids, it is a single stage operation. You are enriching the vapor at only one stage. That means the liquid and vapor are in contact only once. Now, what happens if you can condense the vapor? So, that is going to be richer in alcohol, again evaporated. So, what is going to happen is more amount of alcohol will come into the vapor phase compared to the first stage. So, you are using a second stage. So, the product of the first stage is going to be the feed of the second stage, and what you get out of the second stage, that is going to be even richer in alcohol. So, instead of one stage, you can have multiple stages. So, each stage would give you better enrichment. So, that is the concept of multi-stage distillation process. Now, it is possible that if you use part of the product and let it come in contact with the vapor that is moving up. So, for example, the liquid which you have condensed at a later stage, part of the liquid you are taking out as product, part of the liquid you are giving back to the distillation column. A distillation column is nothing but a combination of number of stages. So, what is a stage? A stage is essentially, it could be the distillation columns are generally circular. So, it is more like a cylinder, and you have number of stages separated by about maybe 2 feet or so the distance. So, one stage is a contacting device where you are going to have intimate contact between the vapor and the liquid. Now, you understand that the contact between the vapor and liquid has to be very, very good, because if there is good contact between the liquid and the vapor, only then more volatile component from the liquid will come from the liquid side to the vapor side. On the other hand, the less volatile component from the vapor side will go towards the liquid side. So, it is a continuous mass transfer across the liquid vapor interface that is taking place on any such stage. So, if it's a continuous separation process that is going on, we all know that the flux, the total amount of transfer is going to be proportional to the area. So, if by some means I can increase the interfacial area between the liquid and the vapor, then I am going to get more mass transfer across the two phases. My aim is to take out the volatile matter, more volatile matter from the liquid state to the vapor state, and the less volatile which is present in the vapor, I would like to bring it back to the liquid stage. So, this is a process which is going on in a counter flow direction, more volatile liquid to vapor, less volatile vapor to liquid. So, enhancement of the mass transfer area, that plays a very important role. Now, how do you enhance the mass transfer area or interfacial area of a liquid vapor mixture? Okay. If a vapor bubble is big, and if you have, instead of one big bubble, 10 smaller bubbles, which one has more area? 10 smaller bubbles. So, your aim would be to break the bubbles, or to make the contact in such a way that you have tiny bubbles in a liquid, and so that in order to do that, your liquid mass has to be agitated as much as possible. So, what happens in that case? Then you have on a tray, these are called trays, each stage is called a tray. On a tray, you have an aerated, highly agitated mass of liquid and vapor, such that you provide large number of interfacial area and very good contact, that means more contact time. And how do you do that? Your liquid comes from the top, from the previous tray to this tray and beyond. The vapor comes from the bottom. Okay. So, the vapor travels from the bottom, and each tray has a number of holes in it. Okay. Through the holes, the vapor will come, it will interact with the liquid, and then the enriched vapor, since it has interacted with the liquid, enriched vapor will travel to the top, right, to the next tray. So, this way the vapor travels, getting enriched at each tray, and the liquid comes down, getting stripped of its more volatile component as it travels from the top to the bottom. So, in a distillation column, you have to supply a continuous, you have to provide a continuous source of vapor which will travel up, and a continuous source of liquid which will travel down. How do you do that? So, the liquid that comes to the bottom, it is going to be heated to generate more vapor. So, the equipment where this is done is called reboiler. You are boiling it again. So, what reboiler does is, you are taking part of the product, part from the bottom as the bottom product, which will be rich in the less volatile component. Part of the vapor which is generated in the reboiler will travel up. Similarly, the vapor which you are going to collect from the top tray, it is going to be condensed, the equipment known as condenser. So, when you condense it, you take one fraction of it out as your top product, the rest liquid will come back to the distillation column again. So, this stream which comes back to the distillation column to provide the downward moving liquid stream, this stream is called reflux. Okay. So, you have reflux, that means part of the top product given back to the distillation column, part of the vapor which is again fed to the bottom of the distillation column, and as they move up on each tray, there is going to be intimate contact between the liquid and vapor, and it is going to get more and more enriched. That is the basic principle of distillation operation. And what is the commonest use of distillation in today in chemical industry? Where you can find distillation? In petroleum, right? So, you start with the crude, and depending on, suppose it is a very large distillation column with 50 trays. So, you can take products from different trays, and depending on where you are drawing your product, you are going to get different streams. Okay. The top would be I mean you can have from aircraft fuel up to what is the bottom product of a petroleum distillation column. It could be tar. Okay. So, depending on what is your feed stream, what it contains more, depending on that you are going to get different products at different locations. But how does it is connected with transport phenomena? Now, whatever happens on a tray in a distillation column is nothing but transport process between liquid and vapor. Now, what is the driving force for one component to move from the liquid to the vapor phase? The driving force for component A, let us say benzene, to go from liquid to the vapor phase. Why would a bottle of perfume, when I open it, my question is, if I open a bottle of a high volatile component, okay, why would you be able to smell it sitting over there? Diffusion. So, there is a concentration difference between the liquid phase and the vapor phase. So, if you have a concentration difference, that concentration difference in turn, the basic root cause is a change in chemical potential. Because of the change in chemical potential, a species moves from one point to another. But if you look at it at overall point of view, it is the concentration difference which drives the more volatile component from the liquid to the vapor.
Between the two phases also, means in diffusion there is of one phase only.
Okay.
And here liquid is getting.
All right. The question is very interesting. What he says is that so far we have associated diffusion between one phase. So, in a liquid, if I put a drop of a dye, solid dye, then the concentration of dye at that near where it is solid is very high compared to a point where it is not there. So, the concentration difference drives that dye from near the solid dye towards every point in the liquid. So, it is basically flow of dye from one point to another in the same medium. So, what is happening here? If you think of dye as the solid, the dye first gets dissolved in water, and once it gets dissolved in water, the interface concentration is going to be, we can approximately say that the interface concentration is going to be the solubility of the dye in the liquid, and then it starts traveling in the medium. So, when we think of a liquid mixture which is being heated or which is brought in contact with a hot vapor stream, you have to provide the energy required for the high volatile component to change phase. Only when it changes phase, then the diffusion starts taking over. So, you are providing, which brings us to our present discussion, you are providing the energy required for vaporizing a part of the liquid. Now, we know when a part of the liquid is evaporated, the more volatile component will come in higher proportion in that drop compared to the less volatile component. So, you have to provide energy for it to change phase, but we know by changing phase I am enriching the vapor with the more volatile component, and after it changes from the liquid to the vapor, it travels by diffusion in sometimes aided by convection as well. So, what in this since we are talking about distillation column, just to give you some idea, you have any idea of how a tray looks like in a distillation column? Probably not. Okay. Now, what our common sense tells us is that if the vapor travels in this direction and liquid comes down from the top, I have to provide some number of holes on the tray. Now, if the holes are big, what is going to happen? The liquid will drain down. If the holes are too small, what would happen? The flow of vapor will not let any liquid come to the next stage. Okay. So, one is called draining, sipping or weeping, in which the liquid will simply go to the next one, and the other when the liquid cannot come to the next tray because of high gas flow rate or small diameter of the holes, there will be accumulation of liquid on top of a tray, which is known as flooding. So, you can flood it, or you can have a condition in which liquid will weep through the holes. Now, if you just have one, so the dimension of the hole is extremely important. Another thing is, that means that you have to decide about what kind of hole you are going to have on your tray based on your liquid and gas flow rates, the relative magnitudes of your liquid and gas flow rates, gas flowing up, liquid coming down. Another point is, on a tray, if you simply provide a hole only, nothing else, what would happen? The gas will bubble through the stagnant pool of liquid. Okay. So, the contact, I would like to increase the contact time between the bubble and the liquid. Now, how would I do that? In order to do that, I would like to force the bubble taking a tortuous path, not a straight path. So, what I would do is, what is generally done is, the commonest example of providing more contact time is known as a bubble cap. So, as the name suggests, if I look at a bubble cap, if this is a solid tray, then an arrangement like this is provided. So, this thing is known as a bubble cap. So, the gas which comes through this will have to change its direction, and then there are openings here which are known as slots. The vapor will come out of these slots, and this portion and the clearance, all there are several considerations which will help one design what would be this height, what would be this clearance. This is a skirt. So, what would be this clearance, and many things will govern about these things, but the vapor will come in this direction and the liquid forms an agitated mass over each bubble. So, this is a mixture of liquid and vapor. It is almost like a foamy solution. More the agitation that you can provide, better would be your mass transfer. So, commonest type of equipment or commonest type of contacting device is known as a bubble cap. So, gas flows in, comes out of the slot, mixes with the liquid and goes to the next tray with identical situation, with identical construction. Now, if this liquid is very foamy, it forms foams very easily, then there is a danger which we will have to think about as well. Now, what should be the separation between two such plates, two such plates or stages? If it is a foamy liquid, would you like to provide more stage, more difference between the two stage, more distance? Obviously, because if the foams reach over to this one, then what you are doing essentially is short circuiting one stage, because you are over here there should be another liquid pool, and the concentration of this liquid pool and this liquid pool should be different. This one being situated at a lower point should be more concentrated in the less volatile component compared to this one. So, if you let the foam, which is a mixture of liquid and vapor, reach the previous or the upper plate, then you are making these two concentrations more or less the same, in other words short circuiting these two stages. So, if it is a foamy liquid, you would provide more separation between two such stages, but you do not really want a non-foaming system. If it is 100% non-foaming, then you are going to have less contact between the liquid and the vapor. So, you want a moderately foaming system such that you have better contact, but not very high foaming such that it reaches the previous or upper plate. So, these are the conditions. Now, so I have liquid coming from the top, vapor travelling to the top. So, at each stage this is duplicated. Now, you are not supplying any energy from outside. So, what happens, the liquid which is here, if you want to vaporize it, you have to provide some amount of energy. Where would that energy come from? I will repeat my question again. This is my tray, let us say a very simplified figure of one tray containing some agitated liquid vapor mixture. I have liquid coming from the top and I am generating some vapor such that I get some amount of enrichment. In order to generate the vapor, as he has suggested, I need some energy from outside, but these are all insulated. So, where would you get the energy from? The reboiler over here is providing vapor, and that vapor comes to the first tray from the bottom, and it contains some amount of liquid. So, the vapor which comes over here, it will create some more vapor. But what happens, this vapor when it comes over here, it is going to provide some more energy. So, this way you are adding some energy to the system. So, for each moles of vapor condensed, how much are you creating, how much vapor are you creating? Or rather, each mole of liquid coming over here, how much vapor are you generating? Would it be same amount? Each moles of vapor which is coming from tray 1 to tray 2, how much vapor are you going to generate? 1 mole or less than 1 mole or more than 1 mole? Why less than 1 mole? There is no loss. Let us assume that there is no loss. So, 1 mole of vapor coming and condensing here, generating some amount of vapor. Will it be 1 mole? Same or different?
Same, sir.
Why same?
Steady state. Otherwise, there will be accumulation.
Let me think of it from an energy point of view. The vapor which is coming, it contains, let us say, 2 components. It is a simplest possible situation, which is a binary distillation column, 2 component mixture. Would the composition of these 2 be the same? Compositions are different. So, this is going to be richer in more volatile component compared to the stream, compared to this stream. Now, what is the latent heat of a stream? It is going to be, simplest possible representation would be latent heat of component 1 multiplied by what fraction it is present in the stream, plus latent heat of component 2 multiplied by what fraction it is present in the stream. So, since these fractions are changing from stage to stage, you may not have exact equality in terms of 1 mole of vapor condensed, for 1 mole of liquid formed, 1 mole of vapor generated. They may not be the same. But in many of the cases, in many simple distillation column design, it is assumed that for each mole of liquid formed, 1 mole of vapor is going to be generated. Okay. So, the stream that goes up and the stream that comes down, this liquid and vapor at each stages are going to be equally balanced. For each mole of liquid formed, 1 mole of vapor is generated. So, that is going to be an example of equimolar flow. So, this is more about some application which you will definitely read later on in greater details. But we let us not think about this system. What I have drawn here is 2 large reservoirs A and B containing component A and B with mole fraction x is 0, x b 0, x a l, this is 0 and this is L, x a l and x b l. And we know these two containers are connected by a very thin tube and the pressures on both sides are the same. If pressures on both sides are the same, whatever flux, whatever flow of A towards right and B towards left that I am going to get is due to diffusion only. Do you agree with that? It is a diffusion only process. Now, I said that the pressure and temperature and volume on these two are maintained same, okay, maintained at a constant value. So, if the pressure, temperature and volume are maintained at the same, are maintained unchanged, what can you say about the number of moles? In a container 300 liter, the volume remains same, the pressure remains same, the temperature remains unchanged. So, even though you have a binary mixture present in it, what can you say about the number of moles? Number of moles will not change. So, if you maintain that condition, but we are having some amount of diffusion from right to left for A and I am sorry, left to right for A and right to left for B. So, if 1 mole of A over a certain period of time diffuses from container A to container B, what can you say about number of moles of B moving in the other direction? They have to be, these two will have to be the same. So, for each mole of A traveling towards the right, 1 mole of B will travel in the opposite direction. That is the case of equimolar counter diffusion. So, equimolar because the number of moles are the same, counter means they are in the oppositely, they are oppositely directed. So, if we are comfortable with the situation, if we know what is the condition that has to be maintained in order to have 1 mole of A moving in the one direction and 1 mole of B moving in the other direction, then what is that, what is the change in our equation which we have seen so many times that you can suggest? NAZ is equal to minus NBZ. So, the condition required for equimolar counter diffusion is NAZ should be equal to minus NBZ, and your flow, if your diffusion or if your movement of each species is going to be governed by the simple equation that NAZ is minus DAB del CA del Z.
So, both sides vapor is there, means only gas.
You have gases on both sides, only gas, no liquid in this case. So, if you are using, if you are having a condition of equimolar counter diffusion, then the right hand side would be 0 and you are simply going to, we can simply use NAZ is minus DAB dCA del Z. Now, this has very interesting applications apart from distillation and all, and what in the rest of the class what we are going to do is we are trying to solve a situation in which equimolar counter diffusion is used, and utilizing the concepts of equimolar counter diffusion, you would be able to find out the concentrations, concentration differences, I mean concentration gradients, contaminations, etc., which are important in chemical industry. So, the situation that we are going to deal with is an ammonia pipeline problem. So, this is ammonia in the pipe and the pressure in the pipeline is roughly 1 atmosphere, about 1 atmosphere. So, I have NH3 which I am denoting as my component A, that is present at 25 degree centigrade and at 1 atmosphere. It is flowing, the flow, the ammonia is flowing in the pipeline. Now, the requirement of the process is such that you cannot have build up of pressure of ammonia in the pipeline. So, in order to ensure that you do not have any build up of ammonia, excess build up of ammonia, pressure of ammonia in the pipeline, you provide a very thin tube. Okay. This is called a vent tube. So, very thin tube is provided in the pipeline. So, it is exposed to atmosphere So, that means you expose it to air, which I am going to call as component B. So, what would the diameter of this tube is 3 millimeter and the length of this L is 20 meters. Okay. You have some amount of flow of ammonia in the pipeline, which is m dot A as 5 kg per hour. So, this is a pipe and this is a vent tube. So, what would happen if your pressure goes up? You simply have flow of ammonia out to the atmosphere. So, that is how you keep the pressure of the ammonia in the pipeline constant. Now, why 3 millimeter? I can provide 30 millimeter diameter tube as my vent tube, even bigger than that. Why do not I provide a larger diameter tube? We will not only lose ammonia to the atmosphere, we are also going to get contamination of ammonia by air. So, by providing a thin tube, I essentially have my safety valve that high pressure ammonia will pass through it, and at the same time the contamination of ammonia with air or the loss of ammonia will not be that much. So, if we are going to consider such a situation, since someone mentioned the word loss, we would like to find out how much loss of ammonia I am going to have if I provide a 3 millimeter diameter tube, and at the same time what is the contamination of air that I am going to have in my ammonia pipeline. The thermophysical property DAB, or I am sorry, transport property DAB is given as 0.28 into 10 to the power minus 4 meter square per second. Now, first of all, tell me, is this a case of equimolar counterdiffusion? You have two large reservoirs, you maintain the pressure and temperature the same. So, it is a case of equimolar counterdiffusion. Each mole of ammonia moving in this direction, it has to be replaced by 1 mole of air coming from the atmosphere to the pipeline. And since the pressures are roughly the same, you do not have any convective flow. The effect of this convective flow is going to be negligible. So, NAX, if this is my x direction, the flux plus NBX, the flux, what would be the sum of these two? Should be equal to 0. And I am also going to express NAX as minus D dCA dx and NBX as minus D dCB dx. Does any question come to your mind when I write these two? Because what I am writing is D in both cases. Okay. So, what is D? D generally I said is referred as DAB, that is diffusion of A in medium B, but in this case you also shouldn't I use DBA in this, where in one case I am having diffusion of air in ammonia, in the other case ammonia in air. So, shouldn't I use two different DABs in these two equations? Obviously, I cannot use. Essentially what I am saying is these two are equal. I am leaving this as an exercise for you to prove that DAB would be always be equal to DBA. So, if you have air in ammonia or ammonia in air, the diffusion coefficient of the two components in the other would be same. You should be able to prove it. All right. So, 1 D would be sufficient in this case. Now, what is going to be the governing equation? I can take a straight Na coming in this direction multiplied by the area, Na going out multiplied by the area at x plus delta x, in minus out. Is there any reaction? No. Is there any accumulation? At steady state, obviously no. So, what I have is d dx of Nax is equal to 0. So, if d dx of Nax is equal to 0, then I say that Nax is a constant. So, if NaX is constant and if I look at at this expression that NaX is minus dCA dx d multiplied by dCA dx, then what I am saying is dCA dx is a constant. So, if dCA dx is a constant, what is going to be the concentration profile? It is a linear. So, if it is a linear profile, I am skipping those because you already know about these things, how to do this. So, if it is a linear one, then NaX can also be written as minus d multiplied by C final minus C whatever at this point divided by L minus 0. Okay. So, it is whatever be the concentration difference divided by L, that is going to be the concentration, that is going to be the constant concentration gradient which is present in the system. So, I can write NaX as dAB, this is flux, this is total amount. So, I multiply it with area Ca0 minus Cal by L. Okay. So, that's if I express it in terms of concentration gradient Ca0 minus Cal by L, and with dAB and A, I get this as my kg per hour of ammonia leaving the system. But if you look at this, is there any question up to this point? But if you look at this one, you would like to find out what is the value of Ca0 and what is the value of Cal. The concentrations are not given in absolute terms. Okay. I have to express this concentration for a gas. How would I express it? In terms of partial pressure. So, I have to express it in terms of partial pressure, and we know that partial pressure is equal to concentration times RT, okay, universal gas constant and temperature in absolute. So, Pa is nothing but CaRT. So, if I substitute that back in this, what I have for NaX is dAB times A by RT Pa0 minus PAL over L, everything expressed in terms of partial pressure. So, this is the expression which I am planning to use, but before I use this, there are certain assumptions which I am going to make, and I will write each of those assumptions, and then we will try to justify why, first of all, why I have to make that assumption, and secondly, whether this assumption is valid or not in the present case. The first one is basically a statement of the problem, which I am going to state is it is a steady state 1D diffusion. These are statements of the problem. So, they are I should not also say that these are assumptions. It is a constant property. Constant property means D is not going to change with concentration in the concentration range that we are working with. It's T and P are constant.
Sir,
yes.
any question from where A came? Yes, sir.
Oh, okay. This capital A only. What I have written over here, this is the flux one. So, when I change flux to total amount, I multiply it with A. So, the first assumption is not an assumption, it is a statement of the problem. So, we need not think about this one right now. The second assumption is important. I have to evaluate my NaX. I know dAB, I know what is the area, RT etc. known to me. Length is given, Pa0 and PAL. These two I have to know when I am thinking of ammonia. So, in the case of ammonia, this Pa0, is it known to me? How do you know that? Let us say you do not know about this assumption. What I am talking about, Pa0 is whatever be the partial pressure of ammonia in the pipe. Do you know that? Depends on the mole fraction of which one? Ammonia. Or depends on what I have in the pipe. If I can say it is essentially ammonia only, would you be able to say what is PA0? What is PA0 in that case? 1 atmosphere. So, I have to make an assumption that I know PA0, I can without having any other extra information, I can only know PA0 if I assume that negligible mole fraction of air in the pipe. That means the air present in the pipe is very small. So, PA0 is essentially 1 atmosphere or the total pressure. Similarly, if I have to find out what is the concentration of ammonia in air, that is PAL, I do not know that, but a atmosphere being a large reservoir, very large reservoir, it is safe to assume that there is no ammonia in air. So, these two assumptions will help us evaluate PA0, PAL, PB0, PBL, etc. So, these are assumptions right now. Okay. We feel that they are correct assumptions, but we will have to come back and check again. And third is which is an obvious one, that is no chemical reaction. If it is a chemical reaction, then obviously I will not be able to use this one, and these are ideal gases. So, this two is important, the rest are more or less a statement of the obvious. So, how do I calculate Na then? I can write, I mean maybe I do not have to do this, you can figure it out, and the answer for this would be 1.46 into 10 to the power minus 9 kilomole per hour. Okay. So, this much amount of ammonia would be lost to atmosphere for the condition stated herein. So, diffusion through a 3 millimeter pipe which is 20 meter long, when the pressures are maintained the same at the two ends, at the two open ends, this much amount of ammonia would be lost to the atmosphere from the pipe. And once these are mole rates, so you can find out what is the mass rate by simply multiplying with molecular weight, which is 17 for ammonia. You have any question? Okay. All right. The next, so this is clear. The next part that we would like to find out is the contamination in the pipe by air. So, the second part that we would like to find out is contamination by air of the pipe, basically what is there inside the pipe. You have evaluated up to this point, this is simply putting the values. How do you proceed? How do you proceed? How do you find out what is the amount of air which is going into the pipe? Okay. So, what should you equate, mass or moles? Can I equate mass? Okay. I cannot equate mass, only the moles I can equate. So, Na would simply be equal to minus Nb using equimolar counterdiffusion. So, you should be able to find out how many mole, the same kgmole per hour of air would be there, and you can find out what is Nb as well, simply Mb times Na or Nb. Okay. So, the answer for this Nb is equal to minus 4.23 into 10 to the power minus 8 kg per hour. Okay. So, this much amount of air will be moving, will be entering the pipe per hour. The third one that I would like to find out is what is the mole fraction of air in pipe? Mole fraction of air in pipe. Now, this I am asking you because this will validate our, hopefully it will validate our assumption. Our assumption was that the mole fraction or amount of ammonia, amount of air present in ammonia in the pipe is very, very small. So, if I can evaluate my mole fraction of air, if I can evaluate mole fraction of air in the pipe, and if I can show it to be very, very small, then that proves the assumption or partially proves the assumption. So, how do you find out the mole fraction of air in the pipe? Any idea? I have my mass flow rate of ammonia, mass flow rate of air which is entering the ammonia pipe through the tube per unit hour.
So that gives us a number of moles entering per unit hour. And we've got NB.
Pardon me? Okay, suppose this NB, the value of that NB is given to you. I mean, Na is equal to minus NB, so it's 1.46 into 10 to the power minus 9 kilomole per hour. Yes, I will answer that question later on. Why, whether or not will it change with time? Yes. What would be the expression for mole fraction of air in pipe? Just tell me the numbers. NB, capital NB divided by capital NB plus what? Which of ammonia? This you are finding out what is XB. Okay, that is mole fraction of B in pipe. You know MA or M dot A. Okay, M dot A is given as 5 kg per hour. So, if I take 1 hour as my basis, then in 1 hour I have 5 kg of ammonia present and whatever this much kg of ammonia, I am sorry, 5 kg of ammonia and this much kg of air present. Divide by molecular weight to each, pardon me. That's very, very small. If compared to 5 kg, it's insignificant. So, you can find out what is going to be XB, and is it clear to all of you? If I isolate 1 kg, I isolate 1 hour worth of ammonia, it's going to be 5 kg, and in that 5 kg I have whatever 10 to the power minus 8, that's the amount of air present. So, I should be able to find out what is mole fraction by dividing each of them by their corresponding molecular weights and then using the formula for mass mole fraction, which is going to be equal to, when you put the numbers, it would be 10 to the power minus 9. So, this is very, very small, almost you can neglect it, and this also confirms our assumption that the presence of air in the pipe is extremely small. A question was asked is, so that's the problem which you can do the rest. The question that was asked is the problem that we have solved is valid only for short time? Is that the question?
So, I am going to ask if it will change with time.
Okay, that means is it going to be valid for short time, or if we allow enough time, will this situation, will these numbers change? Why not? Okay, so I have a, if I think of this problem, it's a continuous flow of ammonia. So, it's not going to change the composition of ammonia with time. In atmosphere, obviously you won't be able to change anything in the atmosphere. But this is important question is in the next class we will solve a problem where these are of finite volumes. These two containers are of finite volumes. So, obviously the solution that we are going to get will depend on time. With time the concentration will keep on changing. So, you can still make a steady state solution which will be known as for initial period. Okay. The solution is going to be valid only for initial period when the concentration change in each of these container is not very large. So, that is the problem. Those kind of problems we will see in tomorrow's class. So, tomorrow one class would be theory and the next class would be tutorial. Thank you. The same way we have done for heat and fluid flow problems, we first tried to build our concepts based on a shell balance. But we have seen before as well that using a shell balance is extremely useful for clarifying our concepts. But when the problem becomes slightly more complicated, especially in terms of geometry, then it would be difficult to imagine or to visualize such a shell and identify all the terms contributing to heat or momentum transfer. So, we have used the same approach for mass transfer as well. So, we started with a shell balance. It is a species balance across a shell of some small thickness, which we made almost tending to 0, and got our differential equation. From the difference equation we got the differential equation, and that differential equation can then be integrated with proper boundary conditions to arrive at the concentration profile. So, if you would like to generalize such a system, can there be an equation which we will be able to use without resorting to that that shell balance approach? This is what we are going to do today. Now, we are going to do species balance. So, if it is species balance, so it should be somewhat similar to mass balance, because what we are doing is nothing but mass balance considering one species and taking into account all the different mechanisms by which that species can come into the control volume. Now, we are going to restrict ourselves to binary systems for this course, and also we are going to add certain other simplifications. This we have not discussed before, and we will probably not go into the details of that, but you can have mass. So far we have seen that mass gets transferred from one point to another by diffusion mechanism, and the diffusion is solely due to concentration difference between the 2 points. But there are other mechanisms, though not as prominent as concentration difference, by which mass can also get transferred. One of it is very interesting, which is due to surface tension gradient. Okay. If you have in a system surface tensions different at 2 different points, and what can be the primary cause for surface tension difference? Is that clear to all of you? Okay. It is just a species balance, the same way we have done for equation of continuity. So, I am writing the equation of continuity for species A inside an imaginary control volume del x del y del z fixed in space. So, it is a fixed in space, fixed coordinate system. So, this is nothing but equation of continuity for A. And rho refers to mass concentration, C refers to molar concentration. What we are doing is conservation of mass for species A inside a volume element del x del y del z fixed in space. So, this equation represents the change in mass concentration of A with respect to time at a fixed point in space as a result of fluxes of mass coming into the control volume, and we understand that this flux can be diffusive flux as well as bulk due to bulk flow, the result of and a contribution from generation or depletion of A inside such a system. So, if I would like to express this in a more compact vector form, then I would simply write del rho A del T plus divergence of the mass flux vector is equal to the reaction by which it is produced. Okay. It is nothing but a simplified form of this. So, if I can write this expression for this equation for A, I can similarly write the expression for B. So, change in mass concentration of B inside the control volume fixed in space is a result of mass flux of B into the control volume and the reaction rate with which B is being produced or destroyed. So, these two equations are going to be useful for us. What happens if we add them up? If we add this, let us think about the first term, del T of rho A plus rho B. What is rho A plus rho B? Net concentration, net concentration of the system. So, we express it simply by rho. So, this becomes del rho del T. Okay. What is N A? I bring to your notice the equations that we already know. I would like to reiterate one more time. This is the mass average velocity. So, the two expressions that I would use maybe I will put it outside as this. So, these are the two equations which I should substitute. This I should substitute in the mass equation, this I should substitute in the molar equation. And if I do that, two completely equivalent equations of conservation of species A can be obtained. So, I am substituting this into my first equation, that is del rho A del T and all plus small n A, and I am substituting capital N A into this equation, which also I have obtained using similar approaches. So, once I do that, two completely equivalent general equations are obtained, which are del rho A del T So, these two equations are equivalent. One is expressed in mass terms, the other is expressed in molar terms. In one case, the velocity used is mass average velocity, in other case the velocity used is molar average velocity. Apart from that, fundamentally there is no difference between these two equations. So, one can use either of these depending on the situation that we are going to deal with. The only restrictions on these two equations are the absence of any other diffusion mechanism that I have discussed before. So, there is no pressure diffusion, no thermal diffusion, etc. So, that is the only restriction we have on this system. Most of the times we are going to deal with this equation